Hello, everyone. Welcome to this talk by Haleh Akrami. Haleh joined us as a summer intern this summer from University of Southern California, and she will talk about multitask acoustic parameter estimation. And with that, Haleh, please take it away.
So can you see my screen?
Yes.
Great. So I'm going to talk about semi-supervised multitask learning for acoustic parameter estimation. I'm Haleh Akrami, and I'm a PhD candidate at the University of Southern California. First, I'd like to talk about my PhD research, which spans the theory and practice of biomedical signal and image processing, machine learning, and data science. In particular, in my PhD thesis, I am trying to address the problems related to limited and noisy data in the training set. So I developed methods for robust machine learning in order to handle the noise in the training data. And also, I focused on uncertainty estimation. This uncertainty can be used in order to evaluate the reliability of our models and also for anomaly detection. This summer, I worked as an intern under mentorship of Gamper at Audio and Acoustic Research Group. And the focus of my project is semi-supervised multitask learning for acoustic parameter estimation. So I'm going to first talk about the introduction and explain about the problem and then represent the baseline method and result. And finally, I'm going to talk about ongoing and future works. So the acoustic properties of the room might impact the quality of speech audio for the listeners. So here, for example, the microphone picks the direct sound wave from the speaker, but also it picks the reflection from the room. And this reflected signal is called reverberation signal. And this reverberation reduced speech quality. And therefore, we are interested in estimating this reverberation in order to give feedback to the speaker, also compare different noise enhancement models. And sometimes these acoustic parameters are useful for other applications, such as mixed reality. So for quantifying the acoustic parameter of the room, there are two important variables that are used in the literature, T16 or reverberation time, which is the time that takes the sound energy to decay after the source is switched off. The second one is clarity or C15, which calculates the ratio between the early diffraction energy and the energy of the late response from the decay curve. So the reverberate signal is a convolution of the input signal with the impulse response room. So if we have the impulse response room, we can estimate C15 and T16 directly, but this is not the case for real-world application. And what we are more interested is blindly estimate C15 and T16 from a noisy environment. And similar to many other applications, the current state of the art for this estimation is has been used using the neural networks. So another parameter we are interested in is mean opinion score. There are many algorithms that has been developed for speech enhancement, removing noise, echo, and reverberation. But these algorithms do not necessarily improve the speech quality as perceived by human listeners. So for that purpose, in the literature, they introduced the MOSES score, which is a grade between 1 to 5, where 5 means very bad quality, and 1 means very bad quality, and 5 means excellent quality. This is a subjective evaluation, and it's evaluated by the human listeners. So the problem we were interested with the problem of having two data sets. One with T16 and C15 labels and the other bitmask labels. We wanted to combine these data sets in a multitask framework to see if predicting this task simultaneously can improve the prediction for each of these tasks. So there are two challenges for this problem. First, the mask score has bias, and this bias comes from the judges. So basically, it means that when judges scoring an audio example, different judges can score it differently and can have their own bias because it's a subjective measurement. And the second challenge is that this new data set, which is combination of the other two data, is partially labeled, and we don't have all the labels for all the data samples. So going to the first problem, there is a recent paper which tried to estimate the judge score aside from the mean opinion score. So this paper had an additional network in which gets the audio spectrum and also the judge ID, and then use this to predict the judge score. But the thing is that in this paper, they showed that when they in the test set, when they input the correct judge IDs, they get improvement. But if they input the random judge IDs, they do even worse than the baseline model. And this is in contradiction. This is in contradiction to what we want, because in most of the current data set that we have, they are crowdsourced. It means that they are judged by different judges, each sample judged by different judges, and then we have over 300,000 judges. And these judges might not rate any of our test samples, so we don't have any access to judge IDs in the test set. So in the literature, the method that targeted the crowdsourced debiasing are in three different methods. The first method is, which is mostly related to classification, is majority voting, in which they simply take the majority of votes, and they showed that this simple but effective method can reduce the bias. The second method is based on David scale model, which assign a variable, which is reliability of the an annotator or the worker, and tries to estimate that variable along the output parameter. This model is also more related to the classification problem. The third types of method is using soft labels. For using soft labels, they instead of directly calculating the one-hot encoded estimation, they calculate the histogram or probability distribution, and they estimate this distribution given by the annotator rather than the one-hot encoding. So this soft labels is used for regression problem as well in emotion detection. So the partial labels is the second problem. Classic approaches for addressing the partial label are using matrix factorization, similar to the recommendation system, in which trying to estimate a low rank estimate of the matrix and fill the missing entries. But in different approaches, there are two types of methods that had been applied. First is that in classification, they simply assume that all unlabeled data are negative, and then they apply a noisy label framework. This method is more effective when you have some prior information about the data and know that most of your labels are negative. The second type of methods are pseudo-labeling, in which you train an initial model with your labeled data and pseudo-label your data, and then use these pseudo-labels as your ground truths in order to train your student model. So this pseudo-labeling applied into classification, multitask classification problem with trimming. Trimming is important because these pseudo labels can be noisy. It's shown that in the literature, the model has two phases. First, it will run the true labels, in the early learning phase, but after that, it starts to memorize the noisy labels and overfit to them. And in the early training phase, the loss value for two labels are low, but the loss value for um, noisy labels are high, and because of that, we can use this fact for trimming our effort. So what they did in this work is that they applied both hard trimming and soft trimming. By hard, I mean that they removed some part of the samples, which has the highest loss, and by soft trimming, I mean that they applied a lower weight to those samples with the higher loss. So moving to our problem, we are trying to address those problems in these two different data sets. The first data is APE data. APE data is total of 2,000 training samples. These samples our sample rate is 16 kilohertz, and the clean speech is taken from TI-MIT, and impulse response randomly selected from Open Acoustic Impulse Response Database. The most data is derived from InterSpeech 2020 Deep Nose Suppression Challenge and obtained in P808 crowdsourcing base subjective testing framework. And it's about 100,000 unique files, both noisy and clean. And then these files pass through 320 unique noise suppression models and model variations in order to get the training. And in total, we have 400,000 files in the training set. And for the tested, we use DNS MOS for all of our evaluations. Here is the baseline model, which is developed by the previous intern and audio and acoustic group. It has 5 convolutional layers followed by an LSTM model and then a fully connected. And it has roughly 51K parameters, so it's a very small model and has been used previously to estimate MOS labels. The performance for this model is the correlation coefficient is 76% for this model, which is much higher than the random chance. And the first method that we tried to address the bias and crowdsource debiasing is we empirically calculated the judge biases and then calculated the debiased MOS examples. First, for that purpose, we calculated the bias of each judge by calculating the average of deviation of each judge was from the MOS score, and then calculated MOS by debiased MOS by subtracting mean of the bias for all judges that rate one specific sample. The problem is that we only had judge ID for a subset of samples, but not all of them. We also tried soft labels. For generating soft labels, we first calculated probability distribution using the raters annotations, and then we calculated the loss using different between this ground truth probability and estimated probability using different divergences. So we used 3 different divergences: KL divergence, KL reverse, and plus KL divergence, and beta divergence. In this simple simulation, which is generated from 2-mode Gaussian distribution, there's a tall mode and a short mode, where the tall mode shows the inliers and short mode shows the outliers. The KL divergence estimates something in between, and the KL plus reverse KL and beta divergence only estimate the tall mode, which means that they are more robust to the outliers if there are any outliers in our distribution. You can also see the definition of beta divergence. Beta divergence apply power transfer to the likelihood, so it downweights the samples with lower likelihood, basically the outliers. So we applied this debiasing and also a soft loss calculation for this MOS estimation. We get a very minimal improvement using reverse KL plus KL divergence. which was giving the best result in all of these methods. With also debiasing, we get in a little bit, but insignificant improvement. And the beta, we tried 5 different beta values. The beta models are still training, so it's not the final result for this experiment. The second thing that we thought about is is this evaluation good enough? Because our test training samples are as noisy as our training. And in the literature, when they try to evaluate these methods, they have either judge IDs for the test set or they have the ground truths for the test cases. We don't have the ground truths by definition because our evaluation is subjective. And having the judge IDs is not very practical. So for that purpose, we thought to evaluate our models using the samples that have more judges, assuming that those samples are less biased. This is the next thing that we are trying. And the next experiment is moving to the multitask model. Then here, instead of estimating MOS, we are estimating 3 labels simultaneously, MOS, T16, and C15, using the same model. The first, our initial results show that the multitask model is doing worse, specifically in MOS, which has the lower performance. Probably it's the hardest task to train, and because the model does not have enough capacity, it reduces the performance for MOS estimation. So we add 2 things in order to address this problem: increase the model size and add some task-specific layers to our network. By task-specific layers, I mean that in 2 different ways. We split the convolutional layers for each task. We have a pre-split architecture in which we split the first or initial convolutional layers and then fuse the rest of the model. And in the post-split architecture, we split the final convolutional layer with the rest of the model. In this table, I mostly reported I've tried many different experiments, but I only reported the experiment which was giving the most promise. So still, you can see this large single task model has the best performance. The large single task model has about twice number of parameters as a baseline. It's 100K parameters. And the single task one still gives the best parameter, best performance for MOS and T16. The multitask performance reduced, but with increasing the model size, it improves a lot, about 6%, but still below the baseline performance. By splitting the model, also it improved the performance, but still below the model performance, which is a split multitask. With combination of these 2, the performance could reach the baseline single task model, but not the large single task model. But the C15 performance is better than the baseline single task model. The next thing we tried was that as we speculate that the hard task gets the most degradation, we applied a weighting to the most label, which was getting the lowest performance. With this weighting, the multitask split model could reach the performance of the baseline single task, although we can see a little bit of decrease in other tasks as we have a very higher weight on the most label. We did not optimize this weight, but maybe with optimizing it, we get a similar performance to the baseline model using of this weighting. We also tried some automatic weighting loss function, which I did not include in this presentation since we did not get any promising result. So the next problem is addressing partially labeled data. Having this data set, which is partially labeled, we first train a teacher model in order to estimate these missing labels. And then after we estimated these missing labels, we can use them as a ground truth to train a second student model. And this is the multitask semi-supervised multitask learning framework. We also added trimming to this framework, different trimming percentages. So with using this multitask semi-supervised framework, and we could get the performance boosting from the multitask model by about 4%. Which gives us the promise that if we combine this with the larger baseline model, we could get a better performance than the baseline model. This model is also still training. So in conclusion, multitask training might improve the performance in some tasks with enough model capacity, but for more difficult task performance, you might degrade in the performance in the multitask framework, and trimming with semi-supervised learning can boost the performance in the multitask learning with partial label. There are also some ongoing experiments that we are trying. The first experiment is that we are having, instead of this acoustic parameter, we are trying to estimate more correlated labels. We have 3 labels, most OVRL, most SIG, and most back, where these labels are speech signal, overall quality, and background noise, which all are evaluated by the human listeners. We have 8,000 samples of these. 8,000 of our training samples has all of these 3 labels. So we first trained a model using all of these 8,000 samples, which is the baseline model. And then we used all of the data. Of course, the performance increases using the MOS because we have the labels for all of the MOS data sets, but it also increases, the performance also increases by 2% for these 2 other data sets, which we don't have any label in the rest of our samples. Another experiment that we are trying is a sequential multitask model. In this framework, we start from the task which has the best performance. Here is C15, and then we move to the next task with a lower weight on C15, and then we finally move to the most, which is the harder task with lower weights on T16 and C15. You can see that with this sequential learning, we finally could beat the performance of the baseline model for the MOS, but for C15 and T16, which are the previous tasks, the performance degrades from the baseline model. And but still, if we didn't do any, we didn't do any optimization in terms of the weights that we apply in the previous task. It is only the baseline model, not the splitted model, which also give more promise for the future experiment of this model. With more task-specific layer, we might have less degradation in C15 and T16 labels. Another experiment that is still running is another semi-supervised framework, which is called cross-study supervision. In this model, we have 2 parallel model, and each model is initialized differently. And with that, we are trying to estimate output of the one model from the other for the samples that do not have any labels. It has a very similar framework to the constructive self-supervised learning framework. Thank you for listening. This is the end of my presentation. I want to thank my mentor, Gamper, and the support of, Hannes Gamper, and the support of, and for the support in this journey, and Audio Acoustic team for this great experience.
Thank you, Haleh. Yeah, are there any questions or comments from the audience? I can maybe add one note here. So it looks like the Haleh, if you go back to the results for most back and OBR. These results are actually quite encouraging. So we noticed a problem with our training set. Can you still hear me okay? Sorry, my network was dropped. We actually only had 8,000 training samples that included all three labels, which there's some error in the which I'm not trying to figure out with Teams why those labels are missing. But this experiment here is that so Haleh spent most of her time working on multitasking speech quality and acoustic parameters, so T60 and C50. And we found that while we could get small improvements with certain methods, it was very difficult to exceed 3 separate models trained for those 3 separate tasks. And it could be that there is not enough mutual information between those different tasks. So later on, we thought we could try 3 more related tasks, which are 3 different labels for MOS, for speech quality. So the overall quality, the signal quality, and the background quality. And what you can see in this table here, despite the fact that it only contains 8,000 samples that actually have all 3 MOS labels, when you train on the entire, even though the entire data set has mostly only MOS labels, you see a small improvement in the SIG and in the back performance. Now, once we figure out the issue with those, most of those missing labels, so we should have many more than 8,000 training samples, it looks like we might actually get a better improvement for SIG and back, which would be a nice proof of concept because basically we could potentially show that including additional training data in this kind of a multitask setup that is missing labels, so it doesn't have SIG and back labels, you can still improve the performance of the SIG and back estimation, which is kind of the goal of the project from the beginning. It just turned out that T60 and C50 in combination with speech quality was maybe a bit more difficult than we anticipated. So point of clarification here, and one of the reasons why some of the results are still partial is because there were some issues with training models on Azure, but results are still trickling in, and hopefully we'll have more to report soon about those experiments. I see Ivan raised. Ivan, go ahead.
Just while we're on this, I assume that in the first table, this 7409 is a %.
Yes.
Yes.
And the second table are the correlation coefficients.
The second table are root mean square error. The first table
okay, the absolute error.
Yes.
Thank you. Thanks.